So today the topic is inverse functions. And so we're going to graph them, we're going to find the domain and the range of them, and we're going to learn really what inverse functions are. So we're going to start with a function that you might be familiar with, and that is this function here. Changes degrees Celsius to Fahrenheit. So if you want to find a degree Fahrenheit, given that it is, let's say, 50 degrees Celsius, you can do that by plugging the Celsius temperature in for x, multiplying it times 1.8, and adding 32. So that changes Celsius into Fahrenheit degrees. So suppose we want to find an equation, though, that does just the opposite of that. That changes Fahrenheit into Celsius degrees. So it works just the opposite of this. And so right now we could write this example as y equals 1.8 times x plus 32. And then the x represents the degrees Celsius and the y represents the degrees Fahrenheit. Well, if we want to find the inverse of that, we want to have the input be Fahrenheit. We want the x to be Fahrenheit, and we want the output to be Celsius. So essentially what we're doing is this. We're going to change the x and the y, what they mean, around. So in this example here, the x was Celsius, but and the y was Fahrenheit. We want to switch the x and the y around so that we have x equals 1.8 times y plus 32. But we want to get the y here by itself so that we could have an equation that changes Fahrenheit, which is what the x is, into degrees Celsius. So I'm just going to solve this equation for y. I'm going to subtract 32 from both sides. And so on the right hand side I'll have 1.8 times y. And on the left hand side here, x minus 32. But then I want to get the y by itself, so I'm going to divide by 1.8, and I'll divide both sides by 1.8, and so I'll have y equals x minus 32 divided by 1.8. And this is the inverse of our original function because it does the opposite. We would write it as the inverse. So f to the negative 1 of x, that means that designates the inverse, equals, and it's x minus 32 over 1.8. So essentially what this means is that if we take a Celsius temperature that we are familiar with, let's say 100 degrees, and I want to change 100 degrees Celsius into Fahrenheit, what I would do is I would plug 100 into our original equation, which is this one here. I would take 100 times 1.8, which is 180, and add 32. And 180 plus 32 is 212 degrees Fahrenheit. Well, if I wanted to work in the opposite direction and I knew I had 212 degrees Fahrenheit, but I wanted to convert that to Celsius, I could plug 212 degrees Fahrenheit into our inverse function. So I would be plugging it into this one here, and I would take 212 minus 32, which is 180, and 180 divided by 1.8 would put me back at 100 degrees. And so the inverse undoes the original function. It just works as the opposite of what the function is. So let's move on. So if we were to just look at their graphs, and I were to graph this original function here, I would have y equals 1.8 x plus 32. We could graph that pretty easily. Let's say each one of these tick marks represents 10. So we have 10, 20, 32 would be about here. And the slope would be 1.8. So I would go up 1.8 every time I go over 1. And I'm kind of estimating here. I'm going to guess that it's going to cross about here. And we're going to have a line that looks something like this if I were to graph this original equation. And then if I wanted to graph the inverse of x, I'm going to rewrite this here as it's 1x divided by 1.8, which is 0.5 repeating x, and then minus 32 divided by 1.8 is about 17.7 repeating. So again, I'm going to be estimating here, but this is going to have a y-intercept of about negative 17, which is going to be about here, and the slope is 0.5, so it's almost a half, up 1 and over 2. And what we're going to have is something that's going to look something like this, or roughly something like that. And this makes sense because there is a line here that looks like this that's called y equals x. That's just a perfectly diagonal line. And you know how in the original problem we switched the x and the y around, and if we switch an x and a y around, then we're going to have points that are in common. Like for example, in our original problem this was the point 0, 32, but on our inverse function we have a point here that's going to be a point at 32, 0. And every point that we have on one graph, if we switch the x and the y coordinates around, like this might be the point 15 and up 10, 20, 30, 40, 50, 15, 50, we're also going to have a point at 50, 15. And these points are inverses of each other. And they're always reflected over this line here, which is y equals x. Because essentially what we're doing is we're switching the x and the y around. So in other words, if we have a point that's 2, 5, the inverse of the point 2, 5 is going to be 5, 2, because we're just switching the input and the output around. And if we take the point, this is not on the graph, but if I just go on any, let's just go back and say these are counting by ones. If I go over 2 and up 1, 2, 3, 4, 5, I'm right here. But the point 5, 2, 1, 2, 3, 4, 5, and up 2 is right here. And you could see that these 2 points are reflections over each other over this line. And that's how the graphs of inverses will always look. In other words, the graphs are always going to be reflected. Graphs of inverse functions are always reflections over the line y equals x. Let's go ahead and move on. So here we have two functions. We have the function f of x equals negative 1/2 x plus 3. And we're going to find the inverse of that function. We're going to graph both of those functions so that we can see that relationship a little bit better. Let's go ahead and graph this first one here in green. The y-intercept is at 3, so we're at this point right here. And then the slope is negative 1/2. And so I'm going to go down 1 and over 2, down 1 and over 2, and I can keep making these points. I don't know if these are showing up very well from your perspective, but if I take all those points and I make this line, it's going to look something like this. And I'm off a little bit, but you get the idea here. That's what the graph of the original function looks like. That's f of x. So what we want to do now is we want to find the inverse of that function. So to find the inverse of this function, which I could say is y equals negative 1/2 x plus 3, the first thing that I'm going to do is switch the x and the y around. So my output will become my input, and my input will become my output. So I'm going to start with x equals negative 1/2 y plus 3. But then it's going to make a lot of sense to get the y by itself. So what I would do is subtract 3 from both sides. And I'm going to have on the right hand side negative 1/2 y equals, and on the left hand side x minus 3. But then I want to get rid of the negative 1/2, so I'm going to multiply this side here by negative 2. I'll multiply this whole side here by negative 2. Negative 2 times negative 1/2, that's a positive 1y. And it's going to equal, if I distribute, negative 2x and then plus 6. And so now I'm going to graph this function, which is the inverse. I could write it as the inverse of x equals negative 2x plus 6. And it's going to have a y-intercept at 6, which is here. And the slope is negative 2. So I would go down 2 over 1, which is right here, down 2 over 1, down 2 over 1, down 2 over 1. And if I graph that kind of freehand, it's going to look something like this. And so they should intersect at this point right here. But if you remember from our last slide that if we have this line here at y equals x, those are reflections of each other over that line. And that's essentially what we want when we find the inverse of two things. And a quick question that we would want to ask is, are they both functions of each other? And they both pass the vertical line test. Every vertical line hits both of them one time. So yes, these are both functions. Now let's take a look at a different situation. We have this function, y equals 4x squared minus 3. And if you remember graphing these, this is going to start at negative 3. And it's 4x squared, which means that we're going to have points at 1, 1 and negative 1, 1. And it's going to be a graph that's a parabola. It looks something like this. And if we are not sure about that, we could go ahead and make a table of values here and just plug in 1. Like if we plug in 0, maybe we should plug in 0 first. If I plug in 0, then it's going to be 0 and negative 3. If I plug in 1 or negative 1, then 1 squared is 1 times 4 is 4, and 4 minus 3. I'm going to get 1 both times. But it's going to be a parabola that's a skinny parabola that opens up like this. Well, let's find the inverse of this function. So right now we have y equals 4x squared minus 3. And again, just like before, we're going to switch the x and the y around. We're going to write it as x equals 4 times y squared minus 3. And now we're going to get the y squared by itself. So I'm going to start by adding 3 to both sides. So on the right hand side, we're going to have 4y squared. And on the left, we're going to have x plus 3. But then I'm going to divide everything by 4. So now I'm going to have y squared equals x plus 3 divided by 4. But then I have to get rid of the squared sign. So we do that by taking the square root of both sides. So the square root of y squared is just y. But the square root of x plus 3 is going to be plus or minus the square root of x plus 3 over plus or minus 2. So I don't need to put the plus or minus down there twice. But I do have to remember that when I take the square root of it, I have to include both the positive and the negative square root of whatever I'm getting, because I don't know if it's the positive one or the negative one. So this is the inverse of the original function. And if I were to graph that, we could make a table of values here. But one number that I'd probably want to plug in is negative 3. Because if I plug in negative 3, then negative 3 plus 3 is 0. And I'm going to get 0 divided by 2, which is still just 0. And so that's the point right here at negative 1, 2, 3, 0. And if I were to plug in, let's say I plug in 1. 1 plus 3 is 4, and the square root of 4 could be 2 or negative 2. And so if it's 2, it would give me 1. If it's negative 2, it'd give me negative 1. In other words, I have a point at 1, 1, and 1, negative 1. And what I'm going to be doing then is developing this parabola that really opens sideways and looks like that, which is really what we want, because as you recall, when we talked about this earlier, these are going to be reflected over this line, and you can see that that's indeed what they are. The other thing that you should probably see here is that they are not both functions. The original one is a function, but the second one is not a function. The blue one here passes the vertical line test, but the red one does not, because when I draw a vertical line, I don't know if it's going to be this one or this one. And that plays out right here. When I plug in a 1, I'm going to get two numbers back out. I'm going to get either a 1 or I'm going to get a negative 1. And so that means it is not a function. So we will continue this on the second video.